So we're going to have to find potential energy in a situation overall, and so it might involve more than just two objects. So here we have three protons arranged so they are 1 nanometer away from each other. And then what's the total potential energy of that situation? So here is a proton, here's a proton, here's a proton, and for them to be 1 nanometer away, it would have to be an equilateral triangle. Alright, and to find the total potential energy, you need to find the potential energy between every pair of them. So let's call this 1, 2, and 3. That means the potential energy, a lot of people write between 1 and 2, potential energy between 2 and 3, and then the potential energy between 1 and 3. And the nice thing is you could just add them up. Okay, so let's just think of between 1 and 2. We're going to have K. They're each going to have a charge of Q, so this is going to be Q times Q, which is Q squared. And it's going to be over the radius here. And I'm going to wait a second before I put in an ugly number like 10 to the negative 9th. So KQ squared all over R. But it's going to be the same for all three because the way that they are, they all have the same charge. And they all have the same arrangement. So we're going to have just 3 of these potential energy terms. And so really this is going to be 3kq squared all over the radius r. Okay, so let's actually crunch the number here. We're going to have 8.99 times 10 to the 9th. The charge is positive 1.6 times 10 to the negative 19th squared. And then all over the radius, which is 10 to the negative 9th. When we crunch that, we get an answer of 6.9 times 10 to the negative 19th joules. So this is a good time to talk about different units of measurement as well. There's another very useful unit instead of joules is called electron volts, and we'll explain more of that when we talk about potential. But basically the conversion is 1 electron volt is the same as 1.6 times 10 to the negative 19th joules. And so this is just kind of equating, hey, compared to an electron, kind of how much energy is this? So if we divide this out, the electron volts we get is about 4.32 electron volts. Okay. So some problems may ask you for both units. Alright, so here's a problem you should pause video and try doing. Suppose we have the same situation but we swap 1 electron for 1 of the protons. What's the new total potential energy? Okay, so here is the solution. Same kind of situation, they're each 1 nanometer apart. The potential energy is still going to be the sum of all them. But let's just think about this. This one right here is going to be negative, this one will be negative, and this one will be positive. Okay, so we're going to have kq squared all over r, but we're going to take away kq squared over r and take away another kq squared over r. And so the total potential energy is actually going to be negative kq squared over r, just plain. So the signs are going to switch and we don't have the 3 in front, we just have a negative in front. Once you crunch the numbers here, the potential energy total is going to be 2.3 times 10 to the negative 19th joules. And that's also negative because there's a negative sign out front. Now as far as electron volts go, you would take that, divide by 1.6 times 10 to the negative 19th. So I've written it here, about negative 1.4 electron volts, approximately, of energy in that situation.